Today's speaker is Professor Ying-li Zhang, coming from Tongji University in Shanghai. He will give a talk about formation of primordial black holes from inflationary models. Okay, please.
Okay, so first I'd like to thank Professor Ying-li for very kind invitations for me to visit Zhang again. I think I visited Zhang more than 10 years ago when I think that time it was in another building. Or still here?
Maybe
that building. Yeah. So that time it's very pleasure to come back again and give a talk here. So maybe most of people don't know me. So my name is Ying-li Zhang. And currently I'm working as professor in Tongji University, which is based in Shanghai, China. And my main talk today is talking about the formation of primordial holes from the inflationary models. And this was a main topic which I worked for the recent several years, and we made several progress on this kind of scenarios. And these are the papers which we have published 3 or 4 of them, and 2 are already accepted, but still need some time, and 1 is in preparation. So the talk is maybe based on the progress of this kind of works.
Q Huang, the left to the next.
The Qingguo Huang in ITP at that time. The CP was his postdoc that time.
Oh, I see.
Yeah. Okay, and this was the first papers which initiated everything. So which were around 2018. Okay, so before I go to the topics, maybe some people have been to Shanghai, some people not, but maybe I can make a very brief tour to Shanghai, but because I'm so bad at say directions, but I can introduce some good food for you. Okay. Okay. So these are the foods. So maybe some of your Korean fans has already known that these are very famous. There are several famous Shanghai food in Shanghai. For example, this Shanghai crab. These are very famous. They are not so huge as this kind of crab from sea, but these are crab from the rivers. It looks like this. And if you come to Shanghai at around October or November, that was the best time for the Shanghai crab. We are after steaming. The main method to eat it is just steam it. When you steam it, you can find that the whole shell is full of kind of the orange. I don't know how to say it in English, but this kind of really delicious this kind of part. This is a very famous food in Shanghai, and also this is a very interesting food, which is the eel, the yellow eel. I think when you come to Shanghai, I think you ate this up, right? We cook this by using this soybean sauces.
Nice.
Yeah, this is a very famous food in Shanghai. And although it has a lot of many good foods, and maybe one of the most famous is this xiaolongbao, and one is this shenzhenbao, where it's all by steaming and it's all by frying. Many very delicious food, but maybe not so friendly to vegetarian if you are vegetarian. But still, you can find many vegetables which are made by purely vegetable, but they mimic this kind of a meat kind of smells.
Is it the eel from sea or?
No, this eel from the river. Yeah, also very different from this kind of the common eel. Yeah, I think this is very special taste if you just taste it. So if everyone wants to come, please come and try these kind of foods. And there are still many things. If you come, I can introduce very good restaurant to you. And I'm good at eating, but not good at tour. Okay, just one small kind of things. Okay, so now go back to our topic about primordial holes. So if you trace back, if you just simply search for the titles of primordial holes on Inspires, you will find that this topic become very hot since 2016. As you see, before that, there's only around 10 or around this number of papers before that. The affiliate, right affiliate, as you can see here, this is 2016. So when this gravitational wave signals were confirmed in 2016, the topic of primary health, there's a huge increase on this topic. So as you can see, in this year, the paper produced were doubled. And the year after that, it is gradually increasing until last year, it's around 160 papers. So these are only the papers which have explicitly this kind of the primary health in their topics, in their titles. So you can imagine how many papers there are. The number is much more than these numbers since 10 years ago. So you may ask what happened. So why people are so interested in this kind of topic right after this question with signals confirmed, and what is the role they can play in the modern physics or in this kind of cosmology and gravity, these kinds of topics. So in fact, this kind of primary health gives you very, very interesting and rich the physical motivations to do these topics. And since my time of this, my talk is limited, I will just mainly mention two of the main motivations to talk about this topic primary health. The moment motivations, as I said, is after this kind of the gravitational wave signals are confirmed. So you know that this Lagrange work in the Kagra, they have already finished this O3 detection, and all this kind of data were released by using this maps. So this is the numbers are the masses of black holes in the unit of this solar masses. So as you can see, so this is 2, 5, 10, 20, 50, and 100. So as you can see, so most of this kind of merged this kind of masses have quite huge masses. As you can see from here, most of them before their merging, if you trace the data back, most of them are or have the masses which is larger than 10 solar masses. And this is one unexpected features. So before this kind of before the detection of the gravitational wave, for example, before we have always have some X-ray detection or something. So at that time, so these black holes have small masses, saying that their masses are around 5 or unit to 1, the same masses, or order 1 solar masses. But a distinguished and surprising features of Lagrange were that they found a very large families of black holes which had huge masses. So most of them, as you can see, they are beyond the mass range of 10 solar masses. And some heavy ones even have the masses, as you can see here, they have 50 or 60 or even 17 or 90 solar masses. This is a very surprising features from the analogs or from analysis of Lagrange data. We don't know where these black holes come from. This is one thing. Another thing is that, so if you really go to details, you will find more features. Another interesting feature is that, so we see Kimura and Yamaguchi in 2023, we did a work in which we project all the masses into this kind of M1 and M2 planes. And also we select the same so from this 91 reported binary black hole candidates, and we found that most of them say in details about the 76 of them satisfy the condition. So one condition is already known, huge masses. And another condition is that their effective spin, saying that their effective spin is smaller than 0.3. So this gives you another of this kind of black hole is that the spin of the parabolas are really very signatures of fixed pricing. This is because that according to our
the previous one, the chi is a spin you said?
Yeah, chi is effective spin. So upper bound is 1. So in most cases, so if you have this kind of black holes which come from the collapse of stars, because stars also have quite huge spin, they're rotating themselves very quickly.
Actually, extremal limit of
Yeah. So in that case, if you assume that this kind of angular momentum of spins are conserved during the collapse of these stars, then this kite should be very huge. It's around 0.9 or so. But this here gives you a really very small this kind of spins are. So we don't know where it comes from. And as you can see, most of them have this kind of spin. And even some of them, as you can see, these circles, these mergers have even effect smaller than 0.1 now. This means that they are really you can think to be very close to static ones, almost no spin now. So we don't know how to explain this kind of features before. So these are two main features, as I said. If I summarize this kind of all these data, we found two features. The first thing is that these merging black holes are very massive. We don't know how this kind of why these kind of black holes are massive. The other thing is that the spin of these black holes are small. So these are in sharp conjunctions with our previous theory that the black holes should come from collapse of stars. So if their masses are large, that means that when they were their masses were even larger. So how this kind of stars can become stable? This is one question. So another is that how the stars can have almost no spin. That's another problem. So these features are in sharp conjunctions with the theory.
Will you explain the lower bound by the H has the lower bound mass? Will you explain?
I think up to now, the lower mass still satisfies this the Chandra cycles this bound. So lower bound had no problem.
But in your presentation file, so
in my presentation file, I mean that these masses are too heavy. Too heavy. I think it's a problem because at first, so if it comes from the collapse of stars, this means that the mass of stars are at least as massive as these black holes.
In the previous page, the primordial black
hole. So that's the reason why we have to use we resort to primordial black holes. Before, up to now, I didn't say that they are primordial black holes. I just say that they are black holes.
I mean that the mass of the primordial black hole could less than 1/400.
Yeah, of course. There's no limits on the mass of primordial black holes. So this is what I will tell you. So, of course, in order to explain these two features, there also exist some other ways. For example, when in the field of astrophysics, people propose some of the so-called population 3, this kind of stars, where they have plenty of this kind of a metal elements in this kind of stars to explain these features. But this is their point of view. But another way to explain these features in a very natural way is that these black holes may not come from the actual physical collapse of these stars, but come from the so-called primordial black holes. The primordial black holes can very naturally realize these two features. So maybe I have a small cartoons to show what are primordial black holes. So we make this axis as the evolution of the universe, and this is the time for the evolutions. For example, we know that up to now there's around 13.8 billion years, which is the current of the universe. And if you trace back, according to the current standard models of cosmology, our universe may have witnessed a big bang in its birth. So after the big bangs, so our universe enters this, the heating, radiation dominant cases. And after this kind of 600 years, the first atoms was made. And after that, it was the metal dominant cases and so on. So up to our a knowledge of this kind of cosmology, the first stars after the death they may become the actual physical black holes. And this kind of period is around 1 million years. So it is already in the late, matter-dominated era during the history of the universes. And these primordial holes are a kind of very old or very, very old holes, which can be born even within the 3 minutes after this kind of the Big Bangs. And this period was really deep inside the primordial age or era of the universes. So that's the reason why they were called primordial holes, because they were born during the primordial era of the radiation-dominated era. And as you can see, so these later maybe you can see the masses of the primordial holes can be of any masses, and they were not bounded at all. If you don't think about this kind of observations, then they are not bounded at all from the pure theoretical point of view. So this is this is to show how old or how primordial these, or why they were called primordial holes, because they were formed in very, very early stage of the universes. And this is a small tip of this kind of primordial holes. So every people know that Hawking, he wrote a paper on 1971, proposed this kind of primordial holes from the collapse of very high curvature perturbations. But if you really trace back to history, you will see that even 4 years before, there was a paper by Zeldovich and Novikov. There were papers published on the Soviet this kind of astronomies. They firstly proposed such kind of mechanism. So they were the first people who really proposed this kind of these primordial holes. And this is Zeldovich and this Novikov.
Can you explain a bit more what spin? Spin is what the angular momentum of a binary system?
I think spin is this angular momentum of their self-rotation.
Two binary systems.
I mean, here you can also say two, or here what I mean is the individual spin.
Individual.
One black hole spin. Individual. This is what I mean here. Because, of course, here, the time effective is this kind of is the one after they are merged. But you cannot explain so many the kind of small spins from this kind of from large, but these kind of so many small spins of their merged these kind of black holes can be only explained by those cases where individually the black holes have small spins. Otherwise, you cannot explain so many. That's the logic. Okay, so we know that primordial holes can explain these features very well. So can they explain the merger rate, which is predicted by the LIGO and Virgo detections? So the first work was done by Sasaki, Suyama, Tanaka, and Yokoyama in 2016, right after the announcement of this gravitational wave by LIGO. And they use this one scenario to estimate the merge rate of these primordial holes. So what they use it for? So since primordial holes were born from the high curvature perturbations, so this means that when they were born, the universe is very, very hot and in their primordial stages. This means that when they were born, they have almost zero initial velocities. Then how to make these black holes to become the binary structures? If we only consider the two-body interactions, then because they have almost zero velocities when they were born, then if we only consider about this kind of motions, they will just directly collide with each other without forming this kind of elliptical orbits. So how to form this kind of binaries? So in this paper, we consider these three-body interactions where you have two close primordial holes and remote ones. And the remote one gives the tidal forces between these two things. And because of this kind of small tidal forces, then this makes this two bodies not to follow the directly collision objects, but forms a very, very flat elliptical orbits. And gradually, when they orbit with each other, they will emit the gravitational radiations so that their orbits will shrink gradually, and then at last they will collide with each other. This is the scenario which they consider. So when you consider this kind of scenarios, and when after they parameterize the long axis and short axis by alpha and beta, and this is what they found. So as you can see, no matter how you say parameterize the elliptical orbit, both of these two lines will cross the regions. So these shadow regions was the predicted merge rate from the Lagrange-Virgo detections. And as I found on this line, this horizontal axis is F. F is the PBH, how can I say? F is the fractions of PBHs over the whole dark matters. When F is 1, this means all dark matters come from the PBHs. So as you can see, when this F goes inside around, among this 10 to the minus 3 to 10 to the minus 2, in this range, these PBH scenarios can very well explain the predicted merge rate of the Lagrange-Virgo detection. So this was the first paper which did such kind of things. And this paper was, after these papers, so these kind of heavy parameter holes draw a lot of attention because they may be candidates to explain the Lagrange-Virgo detections.
Only to understand. So to realize this three-body interaction, the density of black hole should be high, and that's why the primordial period is important.
Yeah, but it's not very high because the formations of black holes or formations of the area with huge, the huge magnitudes of curved accelerations are very rare. They are not very close, but they are, they are close with around, several PCA.
Then I want to understand why primordial time is important. Time-wise, primordial period.
Because they need to enter the horizons during the radiation dominant eras. And in fact, so these primordial holes does not mean that these black holes must be formed during primordial era, but they can be formed during primordial era. As you can see, maybe later I will explain to you, they can span a very wide range of these, masses. So when their masses are not very huge, then they are formed in a very, very early stage. So this is what I can explain to you later. So this is one. So this is one information I want to carry you, that these kind of parameter holes can be a candidate to explain the predicted, merge rate by the Lagrange-Virgo data. So this is the image for parameter holes which have masses larger than 10 solar masses or so. So this is one information. And also, as I said, these kind of black holes can also have a small masses. And why in small masses they are interesting? So let's make this horizontal. So this is the horizontal axis, and as I tell you, this is the fractions of PBHs over the whole dark matter. And we make this to go to this axis. So here, this is the FM. This is when 1, this is upper bound for 1. And another line, this line, is the masses of black holes, or primary black holes. And from these papers from 2021 by Carr et al., they made a review on the current, constraints of the primary black hole scenarios. And then they form this kind of, figures, which gives you all these kind of constraints up to 2021 and how much you can have primary black holes. As you can see, these shadow regions are already ruled out regions. For example, here, these regions were ruled out because you have a strong, say, a lensing effect. These are all comes from the lensing effect. And to this side, this is a small line, it's small masses. The small masses, why they were constrained is that after the Hawking radiations, they may form a lot of the photons, and these kind of the photons emitted from these Hawking radiations will change a lot of will change the distributions of photons. Then this BBN and also may change because of evaporation of small black holes. So that's the reason why smaller ones are also constrained by the observations. So this is up to, as you can see, up to now, so these primary holes, for example, if you see here, if you want to have primary holes around 10 to the -9 solar masses, then their abundance cannot be larger than 1% of the dark matter. So this is how we use these figures. But if you see these figures, then you will find a very, interesting feature is that here, there's almost no constraint at all, seeing that there's open windows for primary holes at the whole dark matters. Why there is such kind of this kind of window? The reason is the follows. So if you calculate the masses of the corresponding Schwarzschild radius of this small, primary holes, then you will find that the effective Schwarzschild radius of these small holes is smaller than the common wavelength of the light, meaning that any kind of this lensing effect in this mass ranges is not effective because there's no lensing effect that coming from the reflections also. So that's the reason why up to now this region saying that 10 to the -10 solar mass to 10 to the -15 solar masses. In these masses, currently, there's no constraint at all for the primary holes as the whole dark matter. So that's the reason why we often use these windows. Or maybe later, if you use this X-ray, this kind of lensings, this can be modified or not. But up to now, there's just an open window in these 5 digitals. So this gives us another very interesting say. Okay.
So Compton wavelength of light is which light?
Of all this kind of light band, which is in this kind of variable light, which is currently used for the lensing this kind of we can say this lensing this observations, cosmic lensing. All the kind of variable band of this kind of light. So this means that if you want to constrain these windows, you have to use if you want to optics, then you have to use X-ray or the other sources which have much shorter wavelengths. Then you may be able to constrain these windows. Otherwise, there's no way. So this gives us a hope that during this open window, 5 digitals in the masses, it's possible that we can consider the scenario where all these kind of dark matters not come from wind, not come from neutrons, but comes from the primary holes. So this is another windows where people were very interested in maybe seeing that the small masses of primary holes may be a seed for the dark matters. And this is another interesting windows for small massive of primary holes.
Mainly you talk about large black holes.
Yeah, that was the large. Yeah.
Why they cannot be dark matter candidates?
Because as you can see from here, if you can see around 10 solar masses or so, then as you can see, they can be dark matter, but very small fractions, because around this huge black holes, you have this kind of lensing this kind of constraint on it.
The color ones are ruled out.
I ruled out, but these are not. These are just from fake data, which is not confirmed at all. But these shaded regions are already ruled out. So from here, it's totally ruled out by the lensing. From here, it's ruled out by the BBN and multi-distortion, some other effects. So this is the current status. As you can see, only here it can be this kind of primary holes counting for all the dark matters. So this is the window where people also like. So to be in all, people like this window because this is PBH for all dark matter, or this windows where we don't need PBH for dark matters, but PBH to explain the like novel detection. So these are two windows which we are the most interested in the current. Of course, you have some others ones, and this can explain the other. For example, in this regions, these are PBH to explain the asteroid, say a planet or so. So this is the current status of this, say, a primary house. Of course, you have many other, say physics motivations. I cannot explain all of them, but these are two main interesting, say regions of primary house which draw our attention. Also, you can also have very huge primary house. For example, 10 to the 7th, 10 to the 5th, or even larger. And this is the primary house to explain the supermassive, say black holes, which, for example, is in the center of the galaxy, also in the center of Milky Way also. So this is another thing. Okay, so that's now, up to now, I talked about why we talk about, say primary house, and then later I will talk about the formation mechanism for this, say, primary house. Okay, so one of the mechanisms to form such kind of primary house is from the enhancement of primordial curvature populations. So in order to explain about this, so let's talk about this, say, space and time diagram. So this axis is this kind of, say, a direction. And because the time directions is the same, and it is in the same directions of the scale factors. So for conveniences, I use the scale factors just on behalf of time. And this axis is the physical lenses of, say, of the, say, physical length of everything. And this lines gives you the evolutions of the Hubble horizons during the whole history of the universe. For example, if we adopt the current standard, say, a cosmology, we know that just around 60 equal numbers of inflation at the beginning of the universes. So during that time, the Hubble horizon is kept almost as a constant. So that's the reason why we have first say the Hubble horizon as a constant here. And after the horizon ends, or after the inflation ends, we know that when we enter into some kind of reheating or some preheating, this kind of process, which is unknown now. So I just wrote this line here. This is some kind of the reheating or preheating, or anyway, the decay of the inflaton of, say, around these areas. And right after it is radiation dominated areas where the Hubble horizon increases like this red lines, and then you have this, say, radiation and matter equivalences. After this equivalent time, your universe entered so-called matter-dominated cases, and up to now. So this is the evolutions of the Hubble horizons in the whole history of the universes. Okay, so we know that up to now, according to this Planck 2018 papers, we know that to now the curved populations on large scales, on CME scales, which means that these kind of, say, these modes of this kind of curved populations with the co-moving, say, lenses larger than 1 megapercent, they were very strictly, say, constrained by the CME observation, saying that as you can see from here, they are very severely constrained in the sense that the whole spectrum of these primordial curved populations can be only of order of 10 to the -9. So this gives you a very small amplitude of the primordial curved populations. That's the reason why only up to 10 years ago, we begin to be able to, say, observe these kind of signatures.
What is the horizontal axis?
Horizontal axis is this kind of time. Oh, this one. This one is K. K is the wavelength. The wavelength. Large K means smaller scale.
So the bulk is the large scale.
Yeah, no, these are small scale. This is the large K. K is 1 over lambda.
Right.
Yeah, so these are, up here is,
the left end.
left is large scale. These are large scale. These are scales, which is, these are, how can I say, these are the constraints on the co-moving lenses, which is larger than 1 megapercent. So this is from the, say, a Prof 2018 papers, where the power spectrum of primordial curvature fluctuations were constrained to be around 10 to the minus 9. So this means that our large scales, you cannot play. They are very serious constraints by this, say, CMB this kind of observations. So this means that the amplitude for these primordial curvature fluctuations is around 10 to the minus 4. So this is our very severe constraints on the amplitude. So, but as you can see, so these constraints loses their powers when you go to sufficiently small scales. For example, here it's around 1 megapercent. If you go to small scales, seeing that if you go to the right-hand side, then as you can see, these kind of say, a constraints become very, very, very weak and becomes almost diverge. So this means that here, if you go to very small scales from 1 megapercent to maybe 1% or 10% also, then there's up to now, there's almost no constraint at all, saying that theoretically speaking, we can consider a possible or several possible bumps on the primordial curvature conditions.
So the box graph, that can be understood the thickness of the line in the right part.
Yeah. So these are small. So these are small scales. These are small scales which is smaller than 1 megapercent.
Right.
And these are scales which are larger than 1 megapercent.
And what is the y-axis?
Y-axis is the amplitude of the power spectrum of this primordial curvature conditions. It's the amplitude of this power spectrum. So this part, the amplitude of here is 10 to the minus 9. So this is very strictly, say,
10 to the minus 9 means what is the 10 to the minus 9?
10 to the minus 9 here. 10 to the minus 9 is the power spectrum of primordial curvature conditions. So if you see the power spectrum of R, is nothing but just this R and R. So this is 10 to the minus 9, means that this kind of amplitude of this R is around 10 to the minus 5. So this is on CMB.
And how should I read the box?
On the box here is the
with the 10 to minus and 10 to minus 5. How can I read out of that?
So here it is 10 to minus 1. Oh, maybe I should enlarge it. So you have here. So this is K, and this is 10. Okay, so this 10 to the minus 1. So this is megapercent to minus 1. So this is 10 to the minus 2. So this means that the scale here is around 10 megapercent. Also, and this is even larger scale. This is 10 to the 2 megapercent also. And you have this kind of power spectrum. And here, this is how the Planck say it is this log 10 to the 10. And times this R. So this is around 3 or so. Then here, this is the current constraint around this period, somewhere here. So this gives you this constraint. This is from this Planck 2018. Sorry, it's too small here. Sorry. This is from 2018 paper. So this means that here, there's no play here. This constraint. Here, nothing at all, no constraint at all. So that's the reason.
Right.
Yeah, so that's the reason why we go to this kind of say the convolving length, which is much smaller than 1 megapercent. Then there's no constraint. That's the reason why I say that here, if you go to sufficiently small scales, no constraint at all. Yeah, that's what I said. So it's very probable. So purely theoretically speaking, you can go from 10 to the minus 9 to 10 to the minus 2 or so. So you may have 10 to the 7th, this kind of bumps in the corresponding say magnitude of the power spectrum. But this is totally theoretically speaking now, because there are no constraints at all. So for those modes which if this kind of say bump is realized, then let's just say, for example, at this A star time, the mode at these small scales, or at this small, say, a convolution wavelengths, its x horizons during the inflation, let's say at A star time, when its x horizons, the amplitude of these say curved variations was frozen, and during the whole relation, during the whole say a inflation, so these are totally frozen, and after and after inflation, it goes into radiation dominations. If these modes enter the enter the horizons during the radiation dominated eras, then all this kind of the whole Hubble patches, because the curved variations is enhanced so much that once it enters the horizons, the whole Hubble patches, all the matters inside these Hubble patches will quickly collapse. And the result of the collapse is the formations of this kind of primordial black holes. So this is the mechanism how the primordial black holes were formed. So the necessary elements or necessary factors to form these primordial holes is the amplitude of this primordial power spectrum from 10 to the minus power spectrum for 10 minus 9 to 10 to the minus 2. This 7 orders of increasement of magnitudes is a necessary block to have such kind of scenarios where primordial holes are formed from the enhancement of primordial curvature variations. So this is the scenarios how to form primordial holes. And the method of a primordial holes is around the same orders of all the energy densities in the Hubble horizons at its re-entries. So this can explain your questions that these kind of primordial holes can have any masses. For example, if you want to primordial holes with small masses, then they will leave the horizons later. And maybe, for example, if you have very small, then they may leave the horizon later and enter the horizons earlier. Then the whole masses or whole energy density in these regions are small. Then you may have a small primordial holes. If you want to have large primordial holes, then you have to leave the horizon very early and enter the horizons very late. Then this area, the energy density contained in the area become huge. Then the masses of primordial holes become huge. So that's the reason why up to now you can have any small primordial holes masses can spread a large range of the masses. That's the reason. Okay, so that's one nature mechanism to form the primordial holes. Later, I will talk about another one. So now, up to now, I will just say concentrate on such kind of mechanism. And if you are familiar with inflations, then if you see such kind of pictures, then you will immediately have one question in mind, because the power spectrum of primordial curvature perturbations is nothing but is proportional to the inverse of the slow law parameters in the single field inflations. Then such kind of huge increasements means that you have to have a period where the potentials is very finely or very hugely fine-tuned. For example, if we can separate this kind of the inflation by two stages, one is at large scales and one is on small scales, then the corresponding potentials have to be fine-tuned in such a way where you have the slow rolls, which this period is only the slow rolls for the CMB scales. But when you go to small scales, then you will meet with an inflection point where the potentials have to be tuned very, very flat, where the slow roll parameters here is 10 to the minus 7 of slow roll parameters here. This means that potential here must have an inflection point saying that it must be very, very flat here. Then this causes a problem that you have to fine-tune potentials to be very flat in the inflection point to create such kind of a huge peak in the corresponding, power spectrum. This was so-called fine-tune problem. And that's the reason why people are talking about the concept of ultra-slow rolls coming from this inflection points. And they have a huge amount of discussion about it, because such kind of inflection point may cause a huge problem, because the back reactions of this huge inflection point is very huge. Whether the variety of ways are affordable or not, or can be used or not, is still in debate here. So that was the fine-tuning problem. If you want to have the formation of primary holes from a single model or single field inflation models.
So essentially, inflection point is the one that enhances the...
Yeah, enhances this one. Yeah, people put this part to be CMB and this part for the small scale. Then you have different, features on the power spectrum. That's what's one way to do this. Okay, so up to now, there are many people. I just list out for example, single field models, which were first started in 1998 by Yokoyama and so on. And although later people also invest in multi-field inflation and topographic models and curvature models around these lines to realize such kind of increasement of these the primordial curvature perturbations. Okay, so I think up to now I want to bring you points how we can realize the primordial holes, the formation of primordial holes in these kind of scenarios. The points, all these kind of models have different features, of course, different details, but all of them share the two common features. The first point is that they must satisfy the CMB observations on large scales. As I said, these kind of CMB scales, which was larger than the 1 megaparsec, these must be realized. And the second thing is that there must be a significant enhancement of the curvature perturbations on small scales, saying that these is main features of the power spectrum to realize primordial holes from this kind of enhancement of primordial curvature perturbations. So providing with these 2 points, so we begin to think about, because according to the observations of this CMB by Planck, we know that the Stanistic models sits in the center of R and S relations. So seeing that Stanistic models can naturally explain the CMB observations very well on large scales. And how we can realize these things, and we think that maybe such kind of realize this kind of enhancement may be realized if we only couple the Stanistic model with a non-minimally coupled scalar field, then we may realize both of them in a fairly simple way. So before you see these kind of models, of course they can explain everything, but the mechanisms are quite complicated. So we want to make simple enough these kind of pictures to both realize these 2 points. So this is the motivations why we studied about Stanistic models in this kind of context. And this initiates us to think about such kind of models, which can be traced back to 2017 with GP and Qingguo Wang, this Mr. Sasaki. So our this kind of setup was very simple. So there's nothing but only a Staubach model here, where R square comes from say a correction term, which is the famous Staubach model. And there's nothing but we only introduce a scalar field here, and there exists a non-minimum couplings between the gravity and the light scalar field by xi field here, and by xi say prime here. And we just simply say expand the potential to the second order. As you can see, we use a minus term here to realize a phantom instability. So why we need this, then later you will see it. Of course, so this is in the so-called Jordan frame, and we can first say make a conformal transformation of this kind of models into the Einstein frame. So in the Einstein frame, the Richter scalar is nothing but linear, the same as Einstein gravity, but a scalars were induced by this R square correction. So this models is equivalent to talking about these actions in the Einstein frame, where you have the Einstein gravity, but a more say a scalar induced by this R square term. So in the Einstein frame, this kind of model becomes a bi-scalar field, where you have scalars of phi induced from the Staubach models, and of course you have the chi field here, and the previous these potentials is transformed into this kind of form because of the conformal transformation. Well, this looks a bit complicated, but if you see the features of this kind of the effective potentials in the signal line here, then you can see that it's nothing but this kind of form. So this is the shape of this effective potential. This x is the directions of the light field phi here, and this is the directions of the scalar phi here. So at first, this kind of phi field, as you can see in here, you have this kind of say not so simple, this kind of say relation between each other. But what I want to tell you is that this phi field at first is massive, and at last, when it goes down around this kind of say scalar field in the directions, the phi is a heavy field, where the chi is a light field. In that case, so the inflation can be divided into two stages. The first stage is that when this phi field is very heavy. So the first stage is like you can simply neglect this chi field, and everything looks similar with the Staubach significations, meaning that this say inflaton just goes around this kind of phi direction, where it has small deviations on this chi field. So this period, the first period, is very similar to the cases of the Staubach say inflation. So this can be used to explain the law scales of this inflation.
There is some easy way to see from the action that the phi field is quite massive.
Yeah, so
while chi is not.
Yeah. So in that case, you can expand both. So expand this phi around here. But because this effect phi is smaller than Planck scale, then you can expand it this way. Of course, there's also some phis here. If you calculate this kind of d square v effective d phi, then you can find its effective masses here.
So capital M is essentially the mass of the phi field.
Not necessarily, but this part dominates. As far as I can see, when phi is large.
Why chi is?
But phi is quite small because you have the suppression factor here.
And you chose so that the
I choose V as here. So this is the effective mass for that chi.
But you chose this with a minus sign.
Yeah, minus sign is because we want to have this kind of the phantom instability here. So that's the reason why. So if this mass is positive, then everything it just that it goes around here. because it is a phantom instability here, then you at last when you goes down and you go to the local minimum at its phi field, then you goes into that way. So this is why we have minus sign, because this is where this phantom effect of the phantom field comes from. As you can see, so at first stage, so it's nothing, when the phi is very large, it's nothing but just a Stravinsky model where it goes from a very flat platform and goes down. But when it goes down, you can see there is still some local minimum around here. Then the phantom instability around here enforces you to change this kind of directions of the rolling down from this direction to that direction. So the whole stage is that in the first stage is nothing but this kind of Stravinsky, this kind of inflation. And after that, you enter into a local value of this of phi, and then you have several oscillations around it. And then the phi field becomes light, and the chi field gradually become larger and larger. As you can see, where phi is small here, then chi field become more and more heavy, and then later it's dominates all this kind of the objects or the orbits of this its motion. So the whole process can be divided into two stages. The first Stravinsky model and oscillations and oscillation objects, you have this kind of a high field domination. So this is the projected this kind of orbits around it. So if you, as you can see, there are several peaks during this oscillation, and because it has some dampings or on the oscillations, then its oscillation amplitude is gradually shrinks. But because of this kind of a peak during the oscillations, if you translate this into corresponding power spectrum, then what you find is the follows. So this is the power spectrum here. As you can see, this K here, this is large scales, these are small scales. As you can see, so this part is fairly flat, so which can be used to explain the CM data around it. And if you go to especially the small scales, you can really find that this is a very huge enhancement from this large scale to small scales. And this peak really comes from this kind of very sharp oscillations around the vacuum expect values on phi field.
And the role of the chi.
Yeah, the role of chi. So the role of chi enables you to have such kind of oscillations around the local minimum of phi. That's this kind of that's its roles. And after these oscillations, your kind of the trajectory of this inflations goes around the chi directions, and somewhere your inflation will end around there.
So when moving the chi direction, there's no it is on state. There is no
Yeah. So that's the reason why you're going there. And there's a problem in this model. I will talk about this. Yeah, this comes from as you said. So these kind of oscillations can really realize a huge peak around the power spectrum from 10 to the minus 9 here, but this is a different normalization now, from 9 to a 10 to the minus 2 around here. So this kind of 7 orders enhancement was realized by choosing different as you can see, I can choose different parameters here, but still this kind of enhancement can be realized. So this means that in our models, there is no fine-tuning problem here. And if you calculate its mass functions, so for example, this kind of PBH fractions or cold dark matters, you will find that it's nothing but proportional to the exponential of 1 over power spectrum. Then this means that 10 to the 7th enhancement here really gives you a huge bump in the corresponding mass function because it's exponentially enhanced. So that's the reason why such kind of peak really gives you a very, very sharp, this kind of, say, almost like a delta function, like this kind of say, peak in this mass function. And you can arrange this to be located in the windows, which I have, say, mentioned, where you can have the parameter holes for all of the dark matters. So that's the way how we realize the parameter holes, formation of parameter holes in such a simple model, where you have the, say, a nominal coupled, say, scalar field, which is coupled with the service models, and such kind of, say, a parameter hole formations can be realized in a very simple way here. So this is what we have already, say, achieved in 2017. But there, in these models, there still exists two fatal defects. The first thing is that there's no exit from inflation, as you explained, as you may say realize here, because as you can see, just when you go along this chi-direction now, no local minimum at the chi-direction. So this means that in these models, there's no end of inflation. This is the one fatal problem in this paper. Another problem is that, so as you can see here, there's almost going up and almost the slope looks like infinite. Why it looks like this one? Just because at that time we calculate the large scales here and small scales here, and we use a very rude discount matchings between large scales and small scales. This is totally artificial and just by hand. So that's the reason why it looks almost the slope looks almost like infinite. So this cannot be true, because we cannot have this kind of k to the infinite, such kind of, say, going up slope. So that was a problem which was not solved during that time. So the fact is no x and no interpretations on the enhancement. So that was the fatal problems, and after I realized this, I have sorted this for several years, how to solve the problems, but I don't know how to solve, because when I look back to our calculations, everything still seems to be fine. I cannot find any way. So later, I just realized that this kind of, say, mechanism have to be improved or have to be changed at least slightly. So later, so in 2014, with my students Xingpeng Wang and myself, we begin to realize that this model is not a continuous inflation, saying that in fact inflations were broken during the first stage and second stage, saying that the first stage that's nothing but just kind of, say, a starving state model, it's fine. But during this oscillations, it's not inflation at all, but the slow law conditions were broken during these oscillations. And after these oscillations, then after a small period of break stage, then the secondary this kind of inflation stage you will realize. So in all, such kind of system, okay.
The question about the break stage. So do all the slower parameters become larger, or some are large and small?
Yeah. So in this case, all these kind of slower parameters become larger than unity. So you cannot use the inflationary, this kind of, say, approximations to do calculation here. That's the reason why. Well, before we thought it's continuous, we didn't consider here. That's the reason why it goes up very deep, very sharply. But last, I found that it's not so simple. It violates the slow law conditions in, or maybe if you see this here, around here, this kind of, say, inflationary, say, conditions were destroyed. So how to do this? So now a true or the correct picture is that you have a two-stage inflationary stage which is intermediate by a broken stage. So this is how this is a correct understanding of the picture. And also, so in order for the inflation to end at its local minimum of the chi direction, then you have to introduce the higher order, the fourth orders here, so that you have a local minimum around here. So now in these models, we can, if we add this kind of chi and chi to the fourth this kind of interactions, then you will find that yes, it is a local minimum here. Then it is possible to end the inflation here. That's how we end inflation. And also we found that we really need to shift this kind of chi field, saying that we need to break the chi, this kind of chi direction, say a symmetry, to introduce a parameter chi zero here. Why we need, oh, I think, I will be quicker. What we need here is that we want to break a symmetries so that, so around this chi direction, so this is the first stage where this chi direction and the phi direction. Phi is nothing but a suffix model's slow law where chi is oscillating around it. So this is the first stage. And the stage 3 is the second stage of inflation. If there's no shift around chi direction, say if it comes from here, then when you go to the stage 3, then your inflation is set on the local here. So on the local top here, then the corresponding power, the perturbations around here is very huge, saying that you may go down a little bit and then go to here. Then such kind of scenarios may cause this kind of topological effects, for example, domain wall around, and we don't want to talk about it. So that's the reason why we introduce another say shift little here, so that we don't need to consider the domain wall projections in this scenario. So this is the whole scenarios, and then we studied everything looks similar but different, saying that at last we ended with this kind of prospection. So these are for the loss, these are for these large scales, these are for the small scales. As you can see, the whole power spectrum is divided into 3 parts. The first part is about CMB, so where we effectively specify the Planck data. And as you can see, this alpha parameter here, so it is a combination of this Kasai. Kasai is a nominal couplings between scalar field and the gradient here. So this alpha is more than 3, saying that it may goes up, but slope is more than 3. Why it is more than 3? This is because that delta phi, if you calculate this kind of say a perturbations around the scalar field, the delta phi is nothing but proportional to a to the minus 3/2. And then this kind of power spectrum at most is the square of this kind of delta phi square, and delta phi square is a to the minus 3. So this gives you the A alpha, which is more than 3. So that's the explanation is why it may goes up, but no more than the slope of k to 3. And then you go to the top, and in some stage when you go to even much smaller, this kind of say a scales, it may also goes down in a certain say a slope beta here. So this is the complete version CMB, and goes up and to the top where you have huge increasement and it goes down. So this is the more physical things, and you can calculate everything numerically by different cosine here, and you can see that numerically speaking, you at most say go to k to the cube enhancement and have some wrinkles there and go down. So this is the correct say a calculation of power spectrum. And of course, we have calculated both numerically and analytically, and you can see these two say ways coincide with each other very well. And of course, you can also tune the parameters here so that they have different peaks, and different peaks means that these parameters may have different methods to explain these PVHs at whole log methods, to explain this kind of a small PVHs and large PVHs. So depending on your this kind of what you want. Also, another interesting thing is that you know that because these kind of gradient waves is nothing but proportional to the second order gradient waves is proportional to the phi square.
Before you make, so let's say
10 minutes. Thank you.
for the large, you keep mentioning the large scale and the small scale. The size of or mass of the primordial black hole, is that determined by small scale or large scale?
Oh no, so it depends on where this comes from. As you can see, these red lines, so their K is smaller. K small means large, this kind of corresponding wavelength. So that's the reason this gives you small K with large masses. And this blue one gives you even smaller masses because the top here corresponds to a large K. Large K means smaller wavelengths. Smaller wavelengths mean that it enters the horizon earlier. To enter the horizon earlier, then the corresponding Hubble radius is smaller. Yeah. So that's how you control how massive this black hole is.
Essentially, the K value at the peak.
At the peak, yeah, determines how large this kind of the masses becomes. Okay, maybe I have to be quick within 10 minutes. Sorry. So, and also you know that the second order Gaussian waves on the right hand side, it's nothing but the product of two curved perturbations here. So we said that before this kind of phi is nothing but 10 to the minus 5, and this is squared 10 to the minus 10. Then this part is very, very small. But when you have this phi from 10 to the minus 4 to 10 to the minus 1, these 3 orders magnitudes, and when squared is 6 order differences. Then the capital phi is the Newtonian potential. Yeah. It's nothing but proportional to that curved perturbations. So this is from, let's see, this is phi. Sorry, that is phi from 10 to the minus 4 to 10 to the minus 1 now.
It's a scalar the curvature of
Yeah. So the phi square is 10 to the minus 8 to 10 to the minus 2. Then you have 6 orders enhancements in the sources. So this really sources and non-negligible induced Gaussian waves here. If you go to the second order in the Gaussian waves, and because its frequency is quite low, you can fix this kind of the amplitude of induced Gaussian waves with the current nanograph or EPTA data. As you can see, they released their data in 2023. These red and these red values are nanograph ones, and blue ones come from EPTA. And you can really calculate the induced waves in your scenarios. And we found that our models coincide with their nanograph and EPTA data very well, especially on this kind of low frequency.
So that is the second order perturbation.
Second order perturbations. First also, this is nothing but 0. But second order, it's induced by this linear perturbations here.
So second order is there is always gravitational constant square in front or not necessarily?
Yeah, it's always phi square.
Phi.
Yeah, this part is the source term. As you can see, when this is 10 to the minus 8, then this totally negligible. But when it goes to 10 to the minus 2,
the kappa is the 2 times.
Yeah, kappa square is just kind of 8 pi g, something like this.
But only so partly in the second term there is a 8 pi g, but the first part term there is no 8 pi g.
Yeah, the first order there's nothing but 0 here. The right side is 0. Nothing can source this kind of waves. Yeah, but if you go to second order, then this gives you a huge source. Yeah, that's about it. So I would say that our model is interesting, that our model gives a very good fit to EPTA data. So this is an interesting thing. But the cause of it is that so the effective E40 numbers is reduced because we need to give the small scales to some E40 numbers. So here on large scales, we give only this kind of E40 numbers to around 30 and 40. So that's the reason why if we trace back to the R and S relations, it still goes out of the contours. As you can see, if we don't have this R-cube term, then as you can see, no matter it's 30 or 40, it's always outside the contact hole here. So in the papers, we propose that maybe simply this R-cube corrections may save this kind of a model. And this year, with this Kim Jin-su and my students, Qingpeng, we really did analyze this kind of R-cube corrections in detail. And we found is that if we tune these Q parameters to around 10 to the minus 5, then no matter it's 30 or 40 equaling numbers for CMB, then it can enter and still be favored by the R and NS relation. So this is the final versions for all these kind of models on the static models for parameter holes projection. So that's it. Okay, later I just need 5 minutes to explain everything. So as you can see, so this is, we complete everything of these models, but if we still go back to see this kind of scenarios, later I realized one problem. What's this problem? So if we go to this picture, so as you can see, this is the whole horizon, no problem. But all these kind of parameter holes, which we have analyzed here, is those parameter holes which enter the horizons after the inflation, saying that these are the parameter holes as documented as we have analyzed here. But there exists the other modes where it exits the horizons at the first inflationary stage and then enter the horizons during the short break stage. These kind of periods may also produce another enhancement, and this was not taken into account in our previous works. So why this is important? This is very important things. Why it's important? So I use this kind of signatures. This is with cartoons which I have, where you have brothers, Kopero, and younger Prof. So why is this interesting? Because if we calculate this kind of the light PPHs, could say a light PPHs here, then in order not to influence this, the BBN contraction, then this light PPH must be very small. I mean, smaller than 10 to the 8 grams. This is very, very small PPH. And you may ask me why this is important, because up to now, all these kind of things had already evaporated away. No, this kind of such small PPH that survive until now. Why is this important? Because these kind of small PPH, if you change the way to think about it, if you change this line, this axis to this kind of energy density around it, then you will feel this is small PPH is very interesting, saying that this line is nothing but just the decay of the energy density of the inflaton. So it decays at 10 to the minus 4 and keeps the constant, and then decay at 10 to the minus, and then decay at 8 to the minus 4. This is the decay of inflation, of inflaton. And all these kind of small parameter holes, when it evolves, when it is formed, it acts like matter, right? So it decays into 10 to the minus 3. So this line 10 to 8 to the minus 4, and this line 8 to the minus 3. Then there is some period where the low inflation, decay of inflations, is the same as small parameter holes. And right after it, there is a period where the whole universe is dominated by parameter holes. So this is a small parameter hole dominated era. And after a period, because the parameter holes are so light that they may totally evaporate away, saying that the radiation dominates the areas of the universe comes from nothing but the evaporations of all these kind of small parameter holes. So this is an explanation where this radiation, dominant area comes from. It comes from the whole, evaporations of parameter holes, small parameter holes. And also you have this large parameter holes, right? This is 8 to the minus 3, and this 8 to the minus 4. Again, so there will be some cross between each other, and then you may realize the meta-dominated areas by purely using this large parameter holes. So you can explain the evolutions of universe from radiation-dominated areas to the meta-dominated areas very naturally using this kind of pictures. So this is why this kind of small primordial host is also very important, because it may be an understanding on where this kind of radiation comes from.
So in that case, the leaking process will be kind of like system.
Well, it depends on how you think about it, because there's all the decay of inflation around here. So this means that it cannot purely come from here, but there's still a short period of reheating here. But how to understand this is we are still analyzing it. But we can explain most of the radiation dominant areas purely by evaporations of these small primordial hosts. So this may totally change our understandings on where this kind of radiation dominant area comes from. And more importantly is that, so this kind of signatures gives us a unique features in the corresponding Gaussian wave power spectrum. So as you can see here, we have a double peak features. And if you just choose some parameters, this can be somehow, say, detectable by using the future LISA or DeCycle, this kind of, say, observations. So this peak comes from nothing but, as I have said here, comes from this peak. So this comes from induced Gaussian waves, which come from this kind of enhancement of the primordial curvature variation. So this is the peak which is here. So this is fine here, it's fine. But before that, you have the evaporations of all these small, say a primordial house. And when they evaporate, all these kind of, say, ice curvature perturbations were converted into the adiabatic curvature perturbations. And this really creates another peak before this kind of, say, this peak. So this is a unique features in the corresponding Gaussian wave power spectrum, saying that if in futures you really observe this kind of, say, double peak features, then it must come from this kind of scenarios. So this is an observational, say, scenarios to distinguish the models from other models. And maybe in the futures we may be able to see this from the LISA or the cycles also. So this is an observational features. Or later, I just don't explain here. And maybe 1 or 2 minutes is devoted to another mechanism. So as I have explained, so the enhancement of primordial curvature variations will definitely induce this kind of, say, signal order Gaussian waves. Then we want to ask another questions. If in the futures, no induced Gaussian wave was observed, can we really rule out all these primordial house scenarios, or rule out primordial house? So my answer is no, because there exists some other primordial house without the implications of the primordial power spectrum. So what I mean by this is that, for example, we may consider another mechanism is the tunneling or the bubble nucleation, or what you call the phase transitions during the very early time. So maybe I just put 1 or 2 minutes to simply mention it. So maybe we don't know what the early universe is. So there may exist some such kind of turning processes during the very early universe, saying that if potentials have this kind of, say, signatures where you have a force vacuum and a true vacuum here, and during this very early stage, there may happen to be such kind of, say, a turning process or the kind of phase transition process coming from the force vacuum to the true vacuum. So when this kind of process happens in spaces, you will form such kind of so-called the bubble structure, where inside bubble you have true vacuum, outside bubble is this force vacuum here. And because of this kind of, say, pressure difference between true vacuum and force vacuum on this bubble wall, then the bubble wall will definitely expand forever, right? This is what we have known. However, if this kind of, say, things changes, for example, when this force vacuum decays, then in some period, theoretically speaking, there may happen that the force vacuum decays and gradually, and then to some period, the outside force vacuum become so weak that it is even lower than the vacuum inside these bubbles. Then the situation may be changed. saying that outside become true vacuum and inside will become forced vacuum. Then the bubble will stop expansions and begin to contract. If such kind of contractions always happen, then at last it will also produce permeable holes. So this is another mechanism that permeable holes may come from the bubble nucleations of the scenarios. Not the question is how to realize such kind of scenario. And in our cases, we found that we use the running of the forced vacuum, saying that we have two fields. One is inflaton and one is instanton. And there exists a numerical coupling between inflaton and instanton. And because chi inflaton here is always running, then if you choose the function of numerical couplings promptly, then you may realize this kind of scenario where at first, at the beginning of inflation, the forced vacuum and true vacuum have the same height, and when inflation goes on, then the forced vacuum will gradually goes up, and in the middle of this inflation, it may go to the top, and then when this keep going down, then this vacuum, forced vacuum, will also goes down, and when inflation ends, say chi equals chi f, then as you can see, this forced vacuum become a bit lower than the true vacuum. In these kind of scenarios, we can realize the running of the forced vacuum so that at last the bubbles stop expansion and then begin to shrink. Why this is interesting? Because if we compare these two scenarios, this is the one which is proposed by Blinken and Hellington in 2017, where they assume that the tunneling processes always gives you, they assume a constant tunneling rate. If it assumes so, then the corresponding mass function of permeable holes is very, very flat, saying that this kind of mass functions may touch the boundaries of the constraints. This means that in these kind of scenarios, you can only have permeable holes which have large masses. But in our cases, we found that if you consider such kinds of numerical couplings, then the corresponding mass function is nothing but in this kind of forms. And this may really gives you a sharp peak in the corresponding mass function, saying that we may also realize the permeable holes for dark matters from the contraction of bubbles. And this kind of scenarios does not rely on enhancement of the primordial curvature perturbations. And this will give us another signatures that if in the futures we don't have any signatures of the induced gravitational wave, but still we cannot rule out the corresponding permeable holes because there's other mechanism to produce permeable holes at whole dark matters also. Okay, so sorry, but this is the summary of my talk. So I just use such kind of picture to summarize what we have done. So if we concentrate on the topics of the permeable holes, there are many interesting physical correspondence in surrounding these topics. For example, this blue light, I just use this to connect the permeable holes with observation. For example, we have the PTA observations, pure permeable holes are dark matters, and permeable holes to explain the gravitational wave from the permeable hole binaries. And also permeable holes may be a seed for the supermassive black holes, and many observations can be connected to concept of permeable holes. And also theoretically speaking, we can also construct this kind of or constrain this inflation models on small scales, saying that PBH may come from this permeable curve perturbations and permeable holes may come from this bubble nucleations also. And permeable holes becomes a bridge to connect both the theoretical aspect and also the observation aspects. And this gives us a very interesting features for us at least to probe the physics on the small scales. And these things cannot be done by any other concepts. So that's the reason why permeable holes is interesting. And hopefully in the future we can get more signatures on its existence or rule out it. Either of them is very interesting. Okay, so that's my talk. Thank you very much.